the not-too-distant future, strange craft will zoom across our skies. These are not UFOs. They're not alien craft from another planet. These are machines developed and built by human engineers and designers. Today's science fiction will become tomorrow's reality. These are the aircraft of the future. What you are about to see is a glimpse into the future of aviation. Winged aircraft as we know them will soon be a thing of the past.
Aviation technology today is probably about to undergo some of the most impressive and revolutionary changes that we've seen since the Wright brothers.
Across the world, designers are racing to create fantastic new aircraft that can fly humans higher, faster, and further than ever before. New military designs. Airliners that can take us to the edge of space and around the planet in minutes. And new propulsion systems that will make the jet engine obsolete forever. One casualty of this race for the future sits abandoned on an airfield. This fighter is more advanced than aircraft in service, but it is already obsolete. It was the loser in the engineering competition of the century. In 1985, the U.S. Air Force demanded a new fighter plane, one that would incorporate the most up-to-date advances in stealth and agility. Two multi-billion-dollar designs by rival companies took to the air in a fight to the death. One was the YF-23. It had diamond-shaped wings. The other was the YF-22. The winner would become the backbone of the U.S. Air Force, the loser, a billion-dollar pile of scrap. A fierce fight was about to take place between the two most advanced fighter aircraft ever built. The test pilots fought to outperform each other. But after the YF-23's wheels touched the ground, it never flew again. With its greater performance and agility, the YF-22 was chosen to take the U.S. Air Force into the next millennium. It is a truly remarkable craft. It will be able to reach speeds and perform maneuvers far beyond the reach of the present frontline fighter, the F-15.
Even though it doesn't look enough radically different from all other airplanes that have been built, it is very much different. The engines, the airframe are all tuned to go fly around supersonic, and it'll be the most maneuverable airplane that's ever flown there.
The key to the YF-22's success is in its advanced composite materials. These absorb radar and give it the same signature as a small bird. Its tail fins sweep back behind the engines to shield the jet exhaust from heat-seeking missiles. To preserve its smooth outline, its own weapons are hidden inside internal bomb bays. Even its fuel tank cap is hidden beneath its shark-like skin. Building and testing any new fighter is a process that would be impossible without the bravery and dedication of the test pilots.
This airplane's been a part of my life for the last 10 years. And getting it to this point and getting it in the air, it actually takes a lot of effort. I'm not sure I got it in me to do it again.
The YF-22 incorporates the latest in thrust vectoring technology. Jet engines are pushed along by their exhaust gases. If these are redirected by adjustable nozzles, the tail of the plane can be pushed around much faster. With thrust vectoring, a fighter can change direction more quickly. The YF-22 was expected to dominate the air for 20 years. But there is a rival on the horizon. It also uses thrust vectoring. This plane may be the ultimate fighter of all time. It may even be faster than the YF-22 and is without any doubt more maneuverable in close combat. This is the Sukhoi 37. It looks like any other fighter, but it can perform impossible maneuvers. Fighter aircraft are traditionally fast, but very heavy, which makes them difficult to turn. The Sukhoi 37 can perform heart-stopping maneuvers that defy gravity. For any other fighter, these maneuvers would be well beyond their flight envelope. They would stall and crash. Thrust vectoring and small canard wings on the nose allow the pilot to throw the Su-37 around the skies like an aerobatics plane. "20 tons of military metal can reverse direction instantly. This amazing agility would give it a decisive edge in combat. On its first public appearance, its pilot issued an open challenge to dogfight against all comers. No one took up the offer. The Sukhoi is master of the skies. But with fighters becoming faster, the pilots are getting left behind. In the search for ever more maneuverable planes, it's the pilots themselves that are now the weak link. To beat the punishing physical effects of high-G maneuvers, the U.S. Air Force looks for a particular type of pilot. The shorter and more compact they are, the higher the Gs they can take. They are now conducting tests to see if women are the perfect shape for the combat pilot of the future. Major Sharon Heiss is one of the Air Force's female officers undergoing G-force experiments to test this theory. This centrifuge at Wright-Patterson Air Force Base can accelerate the pilots from 0 to 7 Gs in 4 seconds.
Sharon, ready to go to baseline?
Ready.
Here we go. We got 5.5 Gs loaded for you for 30 seconds.
Okay.
Most pilots black out at 5 Gs. As the forces increase, blood rushes from the pilot's brain towards her feet. Using special breathing techniques and inflatable pressure trousers, pilots can counter this effect and take much higher Gs than they could if they were unaided. Often as much as 11 Gs.
It's been rumored that the data says that women actually do take the G-forces better, tolerate high Gs better than men.
But it seems there are still physical limits on the maximum amount of Gs that any pilot can take.
You're not going to fly beyond about 10 Gs on a regular basis. Pilots simply, they're human beings. They can't withstand that. What we're doing a great deal of, however, is integrating pilots in with automatic systems. They will not be able to exceed the G-forces, but they can perform a lot of functions that are too fast for pilots to perform by themselves without the help of computers.
Modern cockpits are crammed with the latest computer systems. Soon, the pilot won't even need a joystick.
Steer point. Move steer point.
In the near future, they will be able to fly their plane by simply looking in the direction they want to go.
New steer point.
A low-power infrared beam shines into the pilot's eye.
Flight view.
By analyzing the reflection, a computer calculates exactly where the pilot is looking. Linked to a control system that can also understand voice commands, pilots will soon be able to talk to their planes. Even more astonishing is a development that will allow pilots to fly by thought alone. Electronic sensors mounted in the pilot's headband detect his brainwaves. By concentrating or relaxing, the pilot can manipulate his brainwaves and fly this virtual plane through an obstacle course. His task is to try to steer this fighter through the hoops. A black bar allows him to see if he is thinking left, right, or straight ahead. This simulated flight has no other input, no joystick, no pedals. With techniques like this, pilots of the future will be able to control the most radical aircraft. But the biggest cause of air crashes remains simple human error. And the only way to eliminate human error is to fly without pilots. Right now, unmanned aerial vehicles are one of the biggest areas of research and development in the industry. This 6-foot flying saucer, known as Cypher, is an intelligent surveillance aircraft developed for the battlefield of the future. Powered by counter-rotating blades, it can hover or fly up to 60 miles per hour. Onboard cameras transmit live video pictures back to base. Cypher can identify and track hostile targets, from 100 tanks to a single foot soldier. It can take off, spy, and land without any control from a human pilot. Cypher's most deadly asset is its ability to float through the urban battlefield. It can peek around corners or spy through windows, searching out snipers or terrorists with highly tuned sensors. One day, this machine's descendants may patrol our neighborhoods as robotic policemen. In the future, these may become the ultimate urban warriors.
One of the major motivations for using unpiloted surveillance vehicles is that we don't have to risk a pilot to get into very high-risk situations. We can fly a fairly small aircraft in, take advanced photographs, have them transmitted directly without having to risk the fact that a pilot will get shot down. If we shoot down an unmanned aerial vehicle, it costs a few $100,000 or a few $1 million, but we're not risking a pilot.
But the perfect unmanned vehicle would be completely undetectable. It should be quiet, without a noisy engine. And it should be tiny, perhaps small enough to fly through a window and into a room undetected. To meet this challenge, designers are experimenting with radical new concepts and models.
Pre-flight check, rudder control is good. Elevator control checks, trim is good, throttle check. That's fine, ready for flight. What's the wind speed, Stuart? Here we go.
The AeroVironment Company in California builds miniature air vehicles, or MAVs, for military and civilian use. Their smallest remote-controlled surveillance vehicle is a flying disc just 6 inches across. It's even equipped with its own onboard video camera and transmitter. It's so small that it is completely invisible on radar. This MAV may look like a toy, but it's equipped with a satellite navigation system. With its battery-powered propeller, it will fly for 6 miles.
Some of the components that are quite small on the test aircraft are the flight computer and receiver, weighs only 1.5 grams altogether. The propulsion motor up front is approximately 5 to 7 grams. One of the challenges of making structures this size and just handling them is they're so small that you can't hold them with your fingers, you can't see them clearly with the naked eye, so you do have to work under a microscope, and you do lose lots of parts when you sneeze or you just bump the table, and that's just part of the game.
The same team is also developing miniature helicopters. But there is a major problem in building aircraft this small. As propellers and blades get smaller and smaller, they become aerodynamically inefficient.
As you get down to these smaller sizes, the air molecules seem much larger relative to the wing, and the flying becomes more like swimming through water as opposed to flying through air. Because of these difficulties in aerodynamics, we're looking to nature because nature has solved all these problems with birds, dragonflies, and fruit flies.
Already, flapping wing models have been constructed, but they are always highly inefficient and never generate as much lift as an insect. Duplicating the performance of insect wings is one of the holy grails of aviation. Insect wings are the most efficient lifting devices on the planet. Until recently, the reason for this remained a mystery. At Cambridge University in England, Dr. Charles Ellington has solved the puzzle of how insects generate such incredible lift. It's a quest that has taken him over 25 years.
To build a good mimic of a real insect and how it moves its wings, we studied films, and we came up with this, which of course flaps its wings up and down the way you would expect it to do. It also moves its wings perpendicular to that. Many insects show kind of a figure-of-8 wing motion, and we can do this with these 2 movements. Then you have to control the angle of attack of the wing, and to do a good job, you have to control it at the base of the wing and at the tip of the wing so that you can throw the wing into this cambered profile that you see on the downstroke as the wing moves down, generating lift up like that. And then, of course, you have to flip the whole thing over because on the upstroke, what you have is a reverse camber like that. So the wing's moving up, generating lift again, supporting its weight. But you have to be able to change the shape of the wing all the way from the base to the tip and from the front to the back at every moment of the wing beat.
The technology needed to control and coordinate these 4 different types of wing movement is so complex that it has to be controlled by computer program. Because the model needed to study the movement accurately is so large, the speed of the wings is slowed down to 1 beat every 2 seconds. On a real insect, it would be 20 beats per second. This model exactly replicates the way in which the common hawk moth flaps its wings. But Charles Ellington's team also discovered an unusual phenomenon.
All right, let's have some smoke.
By studying insect wings in smoke, they noticed an unusual vortex was created by the downstroke. This observation solved the riddle of how insect wings produce so much lift. The effect was confirmed by a live moth when it was suspended in a wind tunnel filled with layers of smoke.
As the wing moves down, you've got the very thin, sharp leading edge of the wing moving through the air, and just as if you move a spoon through a cup of coffee, you see the flow swirling off that edge. It separates and just swirls up like that into a vortex. And a vortex is like a tornado or a whirlwind. It's a low pressure region of the air. Things get sucked into a tornado. And so sitting here with the vortex spinning like that, low pressure running all along the wing right here, and this low pressure sucks the wing up. And this is what's producing the extra lift on the wing and getting 2-3 times more lift out of these wings than out of conventional wings.
This machine was never designed to fly. But now that Ellington has unraveled the mystery of insect flight, soon there will be miniature MAVs as small as real insects.
In the near future, 3 to 5 years out, we'll be developing dragonfly-size micro vehicles that will be able to fly down hallways and in windows and in through air ducts.
Packed with tiny electronics, batteries, transmitters, and with miniature cameras for eyes, the cyborg Dragonfly will be a master of disguise. With huge amounts of lift, it will be highly energy efficient, invisible to radar, impossible to shoot down. The only danger it will face will be getting swatted.
Nine, 8, 7, 6, 5, 4, 3, 2, 1.
Cover!
With no pilot to compromise performance, even more unusual craft and propulsion systems have been designed and tested. This incredible machine was originally designed to shoot down nuclear missiles and satellites.
Yeah.
Just 12 inches long, gyroscopically balanced, and with thrusters at key points around its body, it is capable of instant changes of direction.
Cover. Cover. Cover tracking. Cover. Roll. All right.
No airplane could ever catch this machine.
Hey!
In the 1960s, NASA investigated the idea of whether it was possible to fly an airplane without wings at all. The lifting bodies were a series of experimental wingless gliders built during the development of the space shuttle. The cross-section of the aircraft body is the same shape as a wing, producing all the lift needed to fly. These initial low-level tests proved so successful that NASA then built the M2 lifting body. It was carried to 50,000 feet by a B-52 bomber and then released. As with all radical new designs, the tests were very risky. To generate enough lift, these early lifting bodies needed to glide incredibly fast. Weighing 2 tons, the M2 sent its pilot plummeting to the Earth at over 200 miles per hour. Gliding at this speed in such an unusual shape, the lifting bodies were extremely difficult to control. On its fateful 16th drop, the M2 began to roll wildly just above the runway. The craft was destroyed. It hit the ground at 200 miles per hour and rolled 15 times. The pilot survived, but the lifting body program was severely set back. But in a hangar somewhere in California, the lifting body is ready to make a comeback. Barnaby Wainfan is a professional designer who worked on the B-2 bomber. He's turned his attention to the home build market and has resurrected the lifting body design. Even stripped down to maintain its secrecy, the unusual shape is still visible.
The difference really between this and a conventional airplane is we've combined the functions of the wing, the horizontal tail, and the body all in one simple shape. And because it's a short, kind of thick shape, it's very light. With the light weight, I don't need quite as much aerodynamic efficiency because I'm not carrying as much load. So I'm not working the air as hard to lift the airplane.
It looks a bit like a stealth aircraft, but the civilian Facetmobile is designed for simplicity.
It does have some interesting characteristics, the most important of which is that it won't stall and it won't spin. And since stall and spin accidents are still a very common cause of death, actually, in general aviation, that to me was very important because I've eliminated one of the major ways that private pilots get themselves in trouble.
Often mistaken for a UFO, this aircraft may lead to a whole new breed of home-built aircraft. Designers around the world are trying to build radical new aircraft. At this once secret airbase outside Moscow, Russian engineers created what looked more like a flying saucer than a plane. Called Taryelka, it was conceived during the height of the Cold War. This early secret footage shows the first scale model tests. Their methods were low-tech, but the results were remarkable. It looked impossible, but the Taryelka flew.
Russian designers have a tremendous amount of imagination and great capability. They have been working under a difficult condition in recent years because they don't have much money, and therefore it's hard to get things accomplished. But some of the most advanced aeronautical and space system designs have been done in Russia.
The initial tests were so successful that construction quickly began on a full-size Taryelka. Looking like a craft from another planet, it could carry up to a dozen passengers and become the new executive jet of the future. The engines are housed inside the main body. The small wings provide no lift at all. They help stabilize and steer the machine. But shortage of money from the Russian government has already caused work to stop on the Taryelka. A waterborne version was also tested. It was designed to travel just above the surface of the water, using a cushion of air to provide lift for very little thrust. This is called ground effect, something Russian designers had used in their most unusual aircraft. This is the Ekranoplan. Larger than a jumbo jet, it holds the world record for the greatest lift for any aircraft, an amazing 1,000 tons. This astonishing machine is powered by 8 huge jet engines, travels at 300 miles per hour, only a few feet above the ocean, and could carry 1,000 Soviet Marines. Since the Cold War, the project has been crippled by financial problems. Today, the original monster sits in dry dock. A more familiar way to carry hundreds of passengers around the world is the 747. It has carried 1.6 billion people and has traveled more than 20 billion miles, the equivalent of flying the entire population of Los Angeles and New York City to the moon and back. But with passenger numbers expected to double by the year 2010, new airliners twice the size of the 747 are needed to meet the demand. An aerodynamics team from NASA, Boeing, and Stanford University is developing a new super airliner, able to hold 1,000 passengers. So that the full-scale version can use the existing airport facilities, its overall wingspan will have to be no greater than the 747. To create the extra room and the extra lift needed for nearly 1,000 people and their luggage, This design has abandoned the traditional shape of fuselage and wing. It has fused the body and the wing together into a design called the BWB, the Blended Wing Body.
The advantages of this configuration over a conventional airplane with separate fuselage and engines mounted on the wings is both in terms of its aerodynamic performance, its drag, and in terms of its structural weight. So it's lighter and cleaner aerodynamically, and this translates to a predicted fuel savings of as much as 30%.
The blended wing body is a concept over 70 years old. Recently, it was used in the ultra-stealthy B-2 bomber. Only the engine exhausts protrude from this futuristic shape. This concept used to be called the flying wing. The designers knew that it could carry huge amounts of cargo or bombs. But flying wings have no tailplane. Versions such as this YB-49 were highly unstable and almost impossible to control. Not until the introduction of computerized technology did the flying wing become viable again. Many modern radical designs are intrinsically too unstable to be flown by hand.
The technology has gotten to the point that we can now build electronics and flight control systems small enough to fly inside models of this size. That means that we don't have to risk a test pilot on a very new idea. We can, at the very early stages of a program, build something like this and investigate the most critical and unknown issues.
Onboard computer control systems are pre-programmed before each test flight. With 15 flaps and ailerons, the blended wing body needs more than double the number of control surfaces, far more than a human pilot could handle alone. The pilot steers as normal, and the computer then coordinates the numerous control surfaces. With its 17-foot wingspan, the blended wing body model might look like the ultimate in toy aircraft. Yet this design could be the shape of the airliner of the future. For the design team, their first takeoff was a nerve-wracking moment. The success of the whole project rested on the first test flight. If the model crashed, 5 years of work and $4 million would be wiped out in an instant. But the first blended wing body model flight was a complete success. In fact, it was so successful that it demonstrated that this radical shape could outperform conventional designs by a huge margin. Creating a successful new aircraft that first breaks and then reinvents the rules is what every aircraft designer lives for.
We like building things that are different, not changing things a little bit and seeing what happens, but rather thinking about what we'd really like to have happen and starting with a clean sheet of paper.
The greatest challenge of all is speed. Large airliners like the blended wing body will remain subsonic. Concorde is the only existing supersonic passenger plane. Designing an aircraft like this presents an entirely different set of problems. In a classic Cold War sting operation, faulty plans of Concorde were leaked to Soviet spies. Their answer to Concorde, the Tupolev 144, was a flawed design. It crashed in front of the world's press at the Paris Air Show in 1973. Concorde is the fastest passenger jet flying. It cruises at twice the speed of sound, New York to London in just 3 hours. But there are only 14 of them in service. They only carry 100 passengers, and they are very expensive to fuel and service. Concorde is over 20 years old. In that time, no one has taken on the phenomenal task of designing a replacement until now. NASA has recently started work on a new supersonic airliner. Known as the HSCT, short for high-speed civilian transport, it is twice as large as the Concorde and can carry 3 times the passengers.
In order for an airplane to fly at over 2 times the speed of sound, it really has to be shaped kind of like a rifle bullet, long and slender. The nose has to be pointed, the tail has to be pointed to allow the air to come back smoothly together after the airplane parts it in supersonic flight. That's not a very structurally efficient shape.
One of the difficulties with Concorde is that the long pointed nose severely limits the pilot's vision on takeoff and landing.
The Concorde has a nose that actually droops down so that the pilot can see the runway. All the mechanical widgetry required to drop that nose probably weighs 5,000 or 10,000 pounds. If we, on the other hand, can develop an airliner which doesn't require the nose to drop down, then we can save 5,000 to 10,000 pounds and make the airplane much more economically viable. The challenge in having a fixed nose type of aircraft is that, we're asking the pilot to fly an airplane with no windows to see out front, just windows on the side.
In the HSCT, pilots will have to land the airliner without ever seeing the runway. No other aircraft has ever attempted this. 300 lives will hang in the balance. The pilots will have to rely on a fail-safe system of video, radar, and infrared cameras.
If you lose power, what happens to that display? What are your backup systems? How is the pilot going to respond in a failure mode situation?
To test the feasibility of windowless cockpits, an unusual experiment was carried out on a specially modified Boeing 737. Installed in the hold was a blind, windowless cockpit directly connected to the aircraft's controls. Infrared cameras showed the pilots where the runway was. The test pilots attempt to land the 51-ton aircraft without ever seeing the runway.
Flaps are set at 30. Start a gentle flare.
Amazingly, the tests proved that the advanced cameras and sensors could provide even better images than the human eye. After proving the viability of windowless landings, NASA test pilots were then able to fly the HSCT years before one could be built. They programmed the flight characteristics of the HSCT into this simulator, the biggest in the world, the $70 million vertical motion simulator at NASA Langley.
Ready?
Ready.
Motion ready?
Motion ready.
Okay.
Over 120 feet high, the vertical motion simulator can precisely simulate the movement of any aircraft, from a fighter to a supersonic airliner. This is the biggest theme park ride in the world. It is so loud its sound was used as the roar of T-Rex in the film Jurassic Park. For a pilot, it is an invaluable source of information on how new aircraft will handle. Projects like this are funded by NASA because they depend on so much basic research. To go beyond this stage of development, the HSCT will need private investors if it is to turn into reality. Some estimate that over 200 of these superfast airliners would be needed to satisfy the world's airlines. The HSCT might one day be a common sight in our skies, but even this plane will have limitations on its speed.
Commercial supersonic aircraft all use relatively conventional turbine-powered jet engines. That is, they're turbine-based engines, as we call them. If we want to fly much faster than, say, Mach 3 or 3.5, we're going to have to go to different kinds of jet engines.
The jet engine was first invented by England's Sir Frank Whittle in the 1940s. Every jet engine flying today still uses the same principle. Even the biggest and most advanced jet engine in the world, the Rolls-Royce Trent 800, is little different. It can generate 104,000 pounds of thrust and hurl the largest airliners through the skies. It is so robust, it can even cope with 30,000 gallons of water an hour in mid-flight without faltering. But even this ultimate jet engine needs air to burn its fuel. It has an altitude limit. The X-15 is the fastest aircraft ever to fly. In 1967, it flew at Mach 6.7, an incredible 4,690 miles per hour, and reached an altitude of over 60 miles, the very edge of space. If an airliner could fly this high, it would experience virtually zero drag and be able to fly from Los Angeles to Sydney in less than an hour. But its jet engines cannot operate this high, as there is no oxygen to feed them. The X-15 was propelled by a rocket engine. It didn't need oxygen to burn its fuel.
T-minus 12.
Even the space shuttle needs to carry more than its own body weight in fuel to reach the edge of the atmosphere.
5, 4, 3, 2, 1, and liftoff.
The shuttle orbiter weighs a mere 77 tons, but it has to carry 1,785 tons of fuel to lift off. If we want to build airliners that can travel as fast as the X-15 or the shuttle, we will have to develop a completely new type of aircraft, one that flies in and out of space. This new design will take off like a plane, but fly like a spaceship. An exciting new aircraft only possible because of a new type of propulsion.
It's a new concept in propulsion systems, and therefore it's really a concept in propulsion systems that can enable new classes of vehicles completely unlike vehicles that we see today.
Right now, Tom Harsha and the rest of the NASA Boeing team are developing an air-breathing rocket engine prototype called Hyper-X. It will be so powerful that it will shatter all previous speed and altitude limits. Just 12 feet long, the unpiloted prototype will be carried to 100,000 feet by a Pegasus booster rocket used for launching satellites. It will be released and its experimental engines ignited. Hyper-X will use its unusual curved shape to scoop oxygen from the thin air and ram it at high pressure into its combustion chamber. Mixed with explosive hydrogen, it will propel the craft forward at an unbelievable 2 miles per second. The test will last only 7 seconds.
The kind of range for the vehicle design that Hyper-X represents, scaled up to a reasonable sized vehicle, is 10,000 miles. With a 2-hour endurance, you're looking at a 14,000-mile flight, which is about halfway around the world.
White Sands Missile Base, New Mexico. Here, tests are taking place on what might be the single biggest revolution in propulsion ever. Visionary designer Professor Lake Mirabeau is developing a saucer-shaped aircraft that flies on a beam of laser light. A full-sized vehicle of this design might one day carry people around the world or into space. Its power supply and engine remain on the ground.
Lightcraft is a completely new flight transportation concept. You have to imagine highways of light that vehicles would ride upon. You don't need turbines, compressors, combustors. You don't need that technology on these vehicles. The work is done for you by the light.
This light is a remnant of Cold War weapons technology. Housed in this building is the control center of a powerful laser gun that shoots the small craft into the sky.
Okay, copy. The Plivets laser is go for a graphite run. Stand by.
Before each flight, the laser is tested for intensity on a solid block of
5,
graphite.
4, 3, 2, 1, firing.
This highly polished cone focuses the laser beam, vaporizing the air around it. This is then mounted beneath a nose cone. The craft is simple. It has no moving parts, no engine. Focusing the laser beam at the bottom of the craft creates a series of explosions that push the craft skyward. But when Professor Mirabeau first proposed this amazing new concept, no one believed it was possible.
There really wasn't anybody in the academic institution that I was going to that was willing to sponsor this kind of research. So I had to get into this from the back door by actually participating in the Star Wars business.
In 1997, NASA financed the idea. Early tests were held indoors, but after just a few months, it was flying higher than the roof of the lab and had to be moved outdoors. Horizontal wire tests were used to see how far the laser could propel it. Then it was time for the Laser Light craft's first free flight. Professor Mirabeau makes it spin at up to 6,000 revolutions per minute with compressed air to keep the lightweight model balanced during its flight. At this speed, like a spinning top, it stays perfectly centered in the beam until it runs out of power and falls back to Earth. The Laser Light craft is now flying higher and further each day.
10 seconds.
The Plivets laser is arming.
5, 4, 3, 2, 1.
As the model lifts off, the square-shaped laser beam is focused to maintain its power and effectiveness. But the 10,000-watt laser beam could destroy the laser craft if it fails.
The next step is that we have to build a 100-kilowatt laser. And with that laser, we'll be able to fly vertically to the edge of space, say 30 kilometers straight up.
Professor Mirabeau is already conducting indoor tests on this much larger design. In a few years, this laser craft could deliver a small satellite into orbit. And in 50 years' time, the Laser Light craft's descendants might even be as common as the family car.
You'll walk out your door, touch your magnetic levitation belt, and float up, to the vehicle. It'll fly around, pick up a couple of your friends, motor over to a microwave laser boost station. In 10 seconds, you're out the top of the atmosphere, leaving at escape velocity for the moon. At nighttime, all you'll see is this extremely bright flash of light leaving the planet. And people say, well, there goes Frank.
In the future, the only limit will be the designer's imagination.
I think history shows that there has never been limits that last very long. And right now, there are even some people that say that the speed of light is not a limit, which we believe it is today. It probably isn't.
The technologies that will make these amazing vehicles possible are already available.
We've really begun just to scratch the surface of what we really can do in aviation. And I see many, many changes coming about during the next few years based on technology that we already understand.
All around the world, new developments are taking place in propulsion, avionics, and aerodynamics. Developments that will take us far beyond the limits of conventional aircraft. Developments that will make the simple winged aircraft a thing of the past and change the way we fly forever.